As I had discussed in the last lecture, that the next lecture shall be on the effect of diagenesis on reservoirs. So we all are aware that the reservoirs, which are mostly formed by two rocks, that is the sandstones and limestones, they are severely affected by the process of diagenesis. We all are also aware that the process of diagenesis, it involves several activities uh, uh, of chemical reactions taking place, then effect of temperature and pressure. So diagenesis starts as soon as the unconsolidated sediments they start their burial. So from the parent rock, as the weathering and erosion they occur, thereafter once the sediments they get buried, the impact of diagenesis starts. Most of the diagenetic changes they diminish porosity and permeability of a potential reservoir. So most of the changes that occur during diagenesis, they have the ability to reduce the porosity and permeability of a reservoir. So we will see the impact of diagenesis on both the sandstone reservoir as well as carbonate reservoirs. So today first we shall discuss the effect of diagenesis on sandstone reservoir. Now we all know that once the sediments they get buried, due to the overburden pressure, they compact. The grains they undergo compaction, and then they are also cemented. So cementation process takes place. Cement, as I had already discussed with you, is of normally two types: the orthogenic cement and allogenic cement. Now once the compaction and cementation occur, they lead to the destruction of porosity and permeability. Say for example, these are the sediments which have been deposited, and as the overburden pressure increases, these sediments they become compact due to the overlying load. Okay, and this compaction may reduce these pore spaces. Okay, other than that, due to the impact of temperature or due to the chemically active fluids, these grains they may get cemented, and this cementation may also reduce the porosity and permeability. So excess compaction and cementation, it destroys the porosity and permeability, while the solution, this solution is basically the dissolution. Dissolution, chemically active fluids, they dissolve the minerals and grains. So once the uh, chemically active fluids they interact with these grains which are even compact or cemented, they may dissolve out the vulnerable minerals or grains, and then they may enhance the porosity. So we can see here that cementation and compaction they reduce the porosity, while dissolution they enhance the porosity. It has been noted that most of the sandstone reservoirs they have a porosity, average porosity in the range of 10 to 20%, and permeability measurable in millidarcies. The porosity and permeability of a reservoir normally decrease with depth. The same thing over here, that as the depth increases means the overburden pressure increases, the sediment they become more and more compact, and they get more and more cemented. So the precipitation of the cement may lead to the reduction of the porosity and permeability. So with depth, the porosity and permeability they reduce. So you can normally say that the porosity is inversely proportional to the depth of burial. Okay, so porosity of a sandstone can be given by this formula at a given depth. So porosity at a given depth is equal to primary porosity. Normally primary porosity is measured at the surface minus the porosity gradient and that multiplied by the depth of burial. So porosity gradient can be measured in percent porosity per kilometer. So with depth, what is the change in the porosity? Okay, and porosity gradient is very important. Normally, it is one of the most important factors, the porosity gradient, as to how it is changing with the depth. And the main variables that affect the porosity gradient, they are the mineralogy and texture of the sediments, as well as the geothermal and pressure regimes. So mineralogy will decide as to are the mineral grains going to get dissolved, or are they going to get unchanged, unaffected by the pressure depth, by the pressure at a certain depth. The texture means the sorting of the grain. So are the grains well sorted or poorly sorted? So that will also impact the porosity and permeability. Then the geothermal gradient means the temperature. With increase in temperature, the chemical reactions, they become faster, their rate enhances. And once the chemical reaction they become faster, or they are very proactive, then again the porosity and permeability of the rock is bound to be affected. And of course the pressures, with depth the pressure increases, which makes the grains more compact. So we'll see these features one by one. Now if we look at the mineralogical maturity, okay, that the more mineralogically mature the sandstone is, the better is its ability to retain its porosity. It's a very important statement. Now when we say here mineralogical maturity, what does this mean? We all are aware that sandstone is normally derived from the pre-existing rocks, where the sand-sized grains, they are deposited and then they get lithified to form sandstone. But here, from what parent rock are these sand-sized grains derived will be deciding what is the maturity of the sandstone grain. Now, if the clastic grains, they are less transported, they are normally immature or less mature sediments. If they are transported for a longer duration of time, then the more vulnerable minerals which are less stable, they get destroyed, and the more stable minerals remain, so they become more mature. So if you see in this curve, in this plot over here, we have these three types of minerals: the volcanic sands, then the arkose. So this, in this arkose, here the feldspar content is more than or equal to 25%, and then quartz arenites, which have quartz as minimum 90% in them. Now we all are aware that volcanic sands mean the sandstones which have these volcanic glass or volcanic minerals, which are very unstable. They tend to get destroyed very fast in the process, and so the volcanic sands, they are quite immature. Our causes, then we know that feldspar is a mineral which is less mature, which is less stable than quartz. So our causes, they are more mature than volcanic sands, but they are less mature than quartz arenite. And quartz arenites, they are the most mature sandstones. So if let us say that they have similar estimated porosity at the surface, so with depth, as you go deeper, with depth, the volcanic sands, they tend to lose their porosity because of the destruction of these volcanic minerals in them, and as they get destroyed, they become more and more compact, and then they lose their porosity. So here you can see the different type of a gradient. So within almost 3 kilometers, a 40% porosity is reduced to almost 5%. Then the arkoses will definitely be more stable than the volcanic sands, And quartz arenites, due to the presence of silica or quartz, they are most stable, so they can still hold their porosity. They can retain their porosity because they are going to be least affected by the changes in the compaction or the overburden pressure and temperature. So with the increasing stability, you can see that with depth. So if we look at the quartz arenite with depth from surface to almost 4.5 kilometers, there is a change of porosity from almost 45% to not more than 20% or 25%. Arcoses from 45% to 20%, while the volcanic sands, they have their porosity changes from almost 40% to 5%, and this is only because of the mineralogical maturity. So volcanic sands, they are most immature, while quartz granites, they are the most mature kind of sandstones. Therefore their porosity values, they change. So the porosity of quartz arenite definitely will be more than the porosity of Arcos, and it will be more than the porosity of uh, volcanic sands, just because of this feature, that is the mineralogical maturity. You'll have to keep in mind the Bowen's reaction series as well as the stability series. So in the Bowen's reaction series, the volcanic minerals or the sandstones which have these minerals which form first, they weather also first. So due to the changes in the temperature and pressure, those minerals which are unstable, they simply are destroyed, or they changed, and then they lead to the more compaction of the grains. Okay, so uh, texturally mature sandstone or a quartz granite, if these grains are deposited, they will be able to retain much of their porosity. So if the sandstone has lesser amount of feldspar or these unstable volcanic minerals, then it is a better reservoir. If we look at the texture, so texture also affects the gradient, the porosity gradient. So poorly sorted sands with abundant clay matrix compact more and lose porosity faster than the clean, well sorted sand. So if you see over here, what happens is that with the pressure, the clay matrix, the fine grained clay matrix, it tends to get compact. It becomes they have the cohesive forces, and they become quite compact. This compaction leads to the uh, loss of the porosity faster than the well sorted sand. So if we look at this sorting pattern over here, from very poorly sorted to poorly sorted, moderately sorted, well sorted, and very well sorted, if we try to plot the porosity uh, gradient on this scale, so the porosity increases with the increase in sorting, or with better or well sorted grains. Then geothermal gradient, it also affects the porosity gradient of the sand. The rate of chemical reaction increases with temperature. So higher the geothermal gradient, faster is the porosity loss. So here, what is the use of this temperature? The temperature facilitates the chemical reactions which lead to precipitation of certain minerals which block the pore spaces. So if the porosity, if the geothermal gradient is higher, then the porosity loss will be faster. Means if the geothermal gradient is higher, then the chemical reactions will lead to the precipitation of those minerals or probably cements very fast, and they will reduce the porosity in the sandstones. Then the fluids which are in the pore spaces. So for example, let me just draw a schematic diagram that if these are the sand grains, okay, and of course you can see here that there are pore spaces, and let me just fill those pore spaces with something. So those pore spaces can be filled with some fluids. These fluids might be connate water. So connate water is the water which is associated with these pore spaces and which got trapped during the burial of these rocks. So this could be connate water. Then, other than this water, we may expect to have oil. This oil may also be present in the pore spaces. Okay. Or we may also have gases in the pore spaces. So we have three types of these fluids, which could be water, oil, and gas. Now, what happens is that oil and gas, they have also been seen to preserve the porosity in sands. How? Now, we all are aware that water is a champion solvent, and meteoric water, once it falls on the ground, it dissolves several of these gases and becomes chemically active. And on further erosion of weathering of the rocks, it dissolves the minerals in itself. Now, once this water enters the pore spaces of the rock of the sandstone, what does it do? It starts to either precipitate the mineral content dissolved in that water, or it may also lead to the dissolution of the vulnerable or less stable minerals. But once petroleum enters the trap, what does it do? So, say for example, in if this is a trap, and here we have the oil, and then we have the water contact. Now, as the petroleum enters in this trap, the connate water, which is there within the pores of the sands, it does not freely move. Its circulation is diminished. Now, due to this arrested or restricted circulation, either the cementation is stopped, or its rate of precipitation, the rate of formation of cement, is very very slow. It becomes very very slow, which means that once the cementation reduces, once the rate of cementation or the minerals of cementation reduces, if the rate of cementation reduces, it will not be able to reduce the porosity. So it means that if the pore spaces, they are filled in with hydrocarbons or petroleum, then it would help in preservation of the porosity, because that will check the precipitation of the cementing material. So it has been seen that the water saturated sands, they tend to lose porosity faster than oil saturated sands, and if they are the gas saturated sand, they preserve porosity more effectively than the oil. Okay, so this was the different factors that are effective in the changes in the porosity and permeability. Now, another way is the porosity loss by cementation. So whenever we say cementation, means it is the precipitation of minerals which bind the grains. So cementation is another process in the diagenesis, and extensive cementation leads to the loss of porosity and permeability. You can understand why that once the sand grains are there and they are having porosity or pore spaces in between them, or the voids, if the cement starts to get precipitated extensively, it will just fill in within those pore spaces itself, and thus it will reduce porosity and permeability. Normally, three types of cements, they are talked about. First one is the quartz, which is the most common cement, silica. the quartz. It generally grows as optically continuous overgrowth on detrital quartz grains. So in the sandstone, if you have the quartz grain, so for example, we have this type of quartz grains in the sandstone, and is also being precipitated as a cement. So it normally grows as it normally grows like this. So under the microscope, you won't be able to judge whether this is the cement, or is it the framework grain, or the detrital grain of that sandstone, because it becomes optically continuous with the detrital grains. So silica cement occurs where acidic fluids have moved through pores, which means that uh, the dissolution of silica is lesser in the acidic environments. So you should keep this in mind, which is exactly reverse of carbonates. So silica is precipitated in low pH solutions, acidic solutions, while carbonate, it gets precipitated in high pH solutions. So it means that silica cement will normally be found where acidic solutions have moved through the pore spaces, while carbonate cement is found normally where the basic or alkaline solution has moved through. So if you see these pictures over here, you can see that these quartz overgrowths, they are looking like as if this is the original grain, because they are optically continuous uh, with the detrital grains, the quartz cement. Second type of cement is the calcitic cement. That is, of course, a carbonate, calcium carbonate, and it generally occurs as calcite crystals. So in this over here, these arrows, they mark the calcite crystals, and they change the fabric of the rock to the extent that the sand seems to float in those calcitic crystals. We all are aware that the calcitic solubility, it is very high in acidic pH, and it is very low in basic pH. So normally calcitic cementation is the result of alkaline fluids moving through the pores, as I have just explained. The third important type of clay of the cement is the clay minerals, which may be present in a sandstone, whether as a detrital matrix or as an orthogenic cement. So the clay minerals may be present in the sandstones as detrital grains also, or maybe as orthogenic cement also. And clays, they always reduce the porosity and the permeability because of their very fine texture and the ability to compact and have the cohesion amongst themselves. So if you see over here, upon deposition, how the available pore spaces, they get filled in with the different types of cement. So quartz and the carbonate cement, they are normally found at the shallower depths, while we also have the orthogenic clay coating, or the replacement cement over here. So this is a beautiful diagram which shows about how upon deposition, the available pore spaces, they get changed with the increasing depth. Okay, so we all are also aware of the fact that the clay minerals are very complex in their mineralogy and their structure. Normally, three main types of clay mineral groups which act as cement, they are kaolinite, montmorillonite, and light. Of course, there are various other types of minerals, but these three are the main clay minerals. So the kaolinite mineral, it generally occurs as well-preserved blocky crystals within the pore spaces. So if you can see over here, this kaolinite, all these yellowish colored material, it is kaolinite. and it diminishes the porosity of the reservoirs but may have minor effect on the permeability. So it doesn't impact the permeability much, but yes, it reduces the porosity of the reservoirs. And since it is stable in acidic solutions, therefore it occurs as detrital clay in continental deposits. So when we say continental deposit, means that these are all siliceous rocks, the silica bearing rocks, and once they get weathered, their silica content comes into the either meteoric water or the moving groundwater, and it is chemically active, and then it brings about these kaolitic clays, and then they get deposited as the detrital clay in the continental deposits, and also as orthogenic cement in the sands that have been carried by acidic waters. So once these waters which weather the continental rocks which are full of silica, they they come in the contact with such rocks or such sediment, the sands, and then they start precipitating out their kaolinite material within those porous spaces, and it becomes the kaolinite cement. Then next is the elite. So orthogenic elite, it grows as fibrous crystals. So all these red arrows over here, they mark the elite growth, elite cement. So these, they cover the detrital grains. These structures often grow over the throat passage of the pores and severely diminish the permeability of a reservoir. So as I had told you about the different types of pores, if we see at the catenary pores, it has got these throats, and the elite cement, if it starts growing over here over the throat of these pores, so definitely this is not going to allow the passage of the fluid from one pore to other, and it is definitely going to diminish the permeability of the reservoir. They typically form in alkaline environments, and they are dominant detrital clays in most marine sediments, and they occur as orthogenic clay in sands through which alkaline connate water has moved. So previously we were looking at kaolinite as the ones deposited by acidic waters, while elites, they have been deposited by the alkaline solution or the higher pH material. While the third one is the molten melalonite clays, which are formed by the alteration of volcanic glass, extremely unstable material, and they are found on either on the continental or deep marine deposits, and they have the ability to swell in the presence of water. So you can understand, once the molten melalonite clays are there as the cement, and the sands are connate water wet, or they are water saturated, under very almost no circumstances they are going to permit the interconnectivity between the pores. So it severely reduces uh, the permeability. Okay, so we saw how the cementation, they reduce porosity and permeability, but is also another diagenetic process, which is solution. So what does solution do? Solution, it enhances the porosity. So porosity may be enhanced by the solution of cement or grain. So if, let us say, some carbonate cement has been precipitated in a sandstone, and then it that carbonate cement gets in contact with acidic waters, these acidic water will start to corrode or dissolve that carbonate, and then another type of porosity or secondary porosity may develop. So it involves leaching of the carbonate cement and grains, which include calcite, dolomite, siderite, shell debris, detrital minerals, especially the feldspar. So we are seeing over here that all these are vulnerable minerals, they are unstable, and they are very much prone to the leaching under the acidic environments. Leach porosity in sandstone is associated with kaolin, which replaces feldspar as well as occurs orthogenic cement. So kaolinite clays, they are very important as the orthogenic cement in the sandstones. Now we have seen that the leaching of carbonate or the corrosion of carbonate is because of the acidic environment, and also acidic solutions, they facilitate the deposition or the precipitation of kaolinite, which means that these acidic solutions must have some sources, and these sources, they are either the weathering of the continental rocks by the surface waters, or so they become acidic due to that, or the decarboxylation of kerogen, which emits out the CO2, it dissolves in the water, and then it may give rise to the uh, uh, acidic waters. Meteoric waters, which are rich in carbonic and humic acids, they weather the sandstone at the earth's surface, and in several cases the solution porosity or the secondary porosity is enhanced also by fracturing impacts. So once uh, the already cemented and well lithified rock undergoes the solution process due to the chemically active fluids, it may develop secondary porosity, and due to the always increasing overburden pressure, they may develop fractures, and these fractures may cause enhancement of the secondary porosity. So I hope you understood the processes of the changes in the sandstone reservoir porosity and permeability due to the diagenesis. Next, we shall see in the next lecture the impact of diagenesis on the carbonate reservoirs. Till then, take care, everyone.